Hello, and thank you for joining me. My name is Anthony Zadoorian, and this is the Repurposing Grease Trap Waste project for the University of Arkansas Biological Engineering Senior Design course. So, some background information on grease traps. There are a variety of types of grease traps, and the ones we're primarily concerned with in this project are typically implemented outside of kitchens of restaurants or bakeries. Grease and food solids are caught in grease traps to reduce the buildup of solids in wastewater pipelines. Grease traps are used to slow the flow of incoming materials and allow separation by density. The contents of conventional grease traps are heavier food solids, water, and the lighter brown greases. The problem that the team needs to solve. Conventionally, the contents of grease traps are collected by third-party companies and are mainly landfilled. Usually without a high enough inflow of waste, there won't be enough brown grease to make it worth spending the money for separating the component and selling it by itself. This means that much of the energy potential of brown grease is lost because it's never made into things like biofuel or converted into bio oil that can be burned for energy. America produces roughly 1.5 million metric tons of brown grease a year, and brown grease isn't usable without treatment. The proposed system, designed by the group, is to take the grease trap waste and separate it into components, then individually process them to yield brown grease, bio oil, and moisture-controlled potting soil. The processes to accomplish this include separating the brown grease, water, and food solids, harvest the brown grease and begin water treatment, dry the food solids and pyrolyze them to produce biochar and bio oil, mix biochar with topsoil to produce potting soil. Shown here is a three-dimensional representation of the equipment and how it would be laid out in the warehouse that we're implementing. Next is the process flow diagram that was put together by the team. It shows the progression through the system and where the inputs are added and outputs are created. It starts by the collection of the grease trap waste from the client, and then transporting it to the process facility using a truck, which takes fuel. Moving the grease trap waste into the holding tanks, which uses energy for a pump, then running the grease trap waste through a grate for separation of the larger solids. This can be miscellaneous items that fall into the grease trap, or things that get taken in from the floor of the kitchen and then eventually make their way into the grease trap. Then run the grease trap waste through the DAF unit, and transport the sludge and the FOG, which is fats, oils, and greases, and then running it through the centrifuge. Then the food waste and the fats, oils, and greases are separated into two separate levels. The food waste goes onto a grinder and then a dryer, and eventually it reaches the pyrolysis vessel where it undergoes torrefaction, and then it either goes into a holding bin where it can be mixed with the biochar or just sold in bulk. Then the fog waste goes to the heated separation tank where this fog waste or the brown grease is skimmed off of the top. And then it can go down to be put into the brown grease holding tanks and eventually sold to brokers. The first step in the separation process is to pass through the dissolved air flotation tank, or DAF for short. Here on the left is a generic representation of what a DAF will look like. Ours would look a little bit different because due to the small quantities our system is processing, this would be oversized. It can also be seen here on the right-hand side, shown in yellow in the model. It is the first step after the storage tanks which hold the grease trap waste from the truck delivery. The purpose of the DAF is to use pressurized air to create bubbles that float lower density particles so they can be skimmed off of the surface and pushed onto the next process. This helps in two ways. First, to separate the brown grease, which will settle on the top first, then to separate the food solids, which will be taken from the bottom. The oil that comes off of the grease trap waste will be sent to the skimming tank, the brown tank located below the DAF in the model. The rest of the wet food solids that come out will be sent to the centrifuge. The centrifuge Here shown on the left is a two-phase decanter centrifuge, which will take some of the separable water and oil from the food solids. This type of centrifuge separates things based on their density by spinning things very quickly. So the liquids, the brown grease and water, will be separated from the solids, the food waste. The liquids will then be sent to the skimming tank to be treated, and the solids will be sent to the grinder. An adjacent step in the separation process to the centrifuge is the skimming tank, which uses this skimmer. Shown here is a horizontal tube-type oil skimmer, which can be seen here on the model attached to the side of the skimming tank. This works by running a tube across the surface of the tank and pulling the oil up and depositing it into the brown grease storage tank located in the round brown tank located behind the skimming tank. The skimming tank is also where we will take the first steps towards taking care of water treatment that needs to be done and addressing the pH, BOD, COD before we can release it down the municipal sewer. Once clean, the water will be stored in this blue tank for further testing and treatment, and also control of our discharge flow rate so we don't overwhelm the sewer system. Next is the grinder, which is located after the centrifuge that accepts the food solids after they have been slightly dewatered by the centrifuge. Its purpose is to grind the dewatered food waste so the average particle size is small enough to effectively be dried and then pyrolyzed. Shown here on the left is what's known as a sludge grinder. This is what's used to grind things that still have a somewhat high moisture content before they go on to the next drying step. Next is the dryer. Here shown in the middle is a general representation of a drum dryer. That will be what is needed to dry the food waste particles, which will still essentially be a sludge before drying process. For our specific system, a specific fan and heater were sized and were chosen based on the energy transfer needed to dry the food waste at the expected moisture content. This can be shown here in figure 5, which is a duct fan needed to move the hot air using the heater shown in figure 7. After the dryer, the food solids reach their last step, which is the pyrolysis step. The dried food solids are moved into the pyrolysis vessel where they will be made into biochar. Shown here in the model in red is a pyrolysis vessel. This system is using slow pyrolysis, sometimes called torrefaction, which occurs at a slightly lower temperature over a longer period of time. This results in maximizing the product of biochar and minimizing the other products of bio-oil and syngas. The biochar is sent to the biochar storage to be mixed and made into the potting soil. The bio-oil is sold in the commodities market as a revenue stream. Now we have the first step in the bagging process, the auger and the bin. These will be used in moving topsoil from outside inside to the batch mixer and then on to the bagging machine. The mix can be fed from the gate on the bottom of the mobile bin and into the hopper on the top of the auger to load it into the various equipment. Next, we have the batch ribbon mixer, which will be located inside, as it can be seen in the model shown in green on the right-hand side. The ribbon mixer will be used to evenly and quickly combine the biochar and topsoil to make our potting soil mix shown here in green. I will touch more on how this is used when I summarize this green bagging system. The last step in the bagging system is the bagging machine. Seen here on the right in the model, and also on the left-hand side is the real-life example. This uses a PLC and sensors to dump a selected amount of the mix into a bag from the hopper on the top of the machine. It then passes down the conveyor where it gets sealed, and then an employee who is running the machine can load it onto a pallet. So, in summary, The bagging part of the system can be seen in this diagram of the warehouse in green. The process starts outside in the topsoil storage bin, which is made out of precast concrete walls and will usually be covered with a tarp. Topsoil is then moved inside to the batch mixer using our mobile bin and the auger. The biochar storage is located in this green storage bin between the pyrolysis vessel and the batch mixer. This is inside to minimize moving hot materials around the warehouse, but also to keep the biochar out of the elements. Then the mixture is moved again with the mobile bin and auger to the bagging machine where the potting mix is packaged and loaded onto pallets so it is ready for distribution. As a major part of the design process for this project, the team evaluated the environmental impacts of the proposed system. This can be summarized in three main topics. First, the localized location of this proposed system versus driving to a regional processor. This included analyzing the distance driven by the trucks for picking up and transporting the grease trap waste for the comparative current system and the new proposed system. The current system sends most of the grease trap waste to a regional processing center that requires much more trucking. Next is avoiding the emissions from the landfill. At the regional centers, the grease trap waste is sent through a centrifuge to take out some of the water, and then the remaining waste is combined with sawdust and then landfilled. This contribution to landfilling will usually contribute to the emissions that can damage the environment. These had to be quantified by the team to compare the positive effects of the new proposed system. Another environmental impact that needed to be considered was the emissions that are produced as a byproduct of making the new equipment for the proposed system. The existing system did not need this calculated because the emissions have already been made. The team determined that the proposed system had a very significant reduction in carbon emissions in a year-to-year basis. The team analyzed the social impacts that would result from implementing the proposed system. This can again be summarized in three main topics. First, the new facility would produce several new local jobs. Second, the smell. A large factor in processing the grease trap waste is the smell. This has an effect on all the neighbors. Our system has been designed to try to use mostly closed containers and minimize the amount of material that is left open to the air, which carried the smell to the surrounding area. Third, this process could also assist the client in improving their public image, using the emission reductions to show they are making steps to be more environmentally friendly. Also by producing a product that could repurpose a local waste source rather than sending it to a landfill would appeal to customers. Last is the economical analysis of the system. This system was found to have overall savings for our client and be cost-effective and efficient. The economic success of this system was judged based on the current price of paying for the grease trap waste collection service and how it compares to paying for establishing our proposed system. Our system was found to be successful in the economical and be more economical and even returning the client some positive revenue streams to help offset the cost of the system. Now to discuss some other alternatives that were considered by the team. Some other considerations were taking the separated brown grease and adding value by processing it into biodiesel. Because the system is based on a local range of grease trap waste collection, the amount of brown grease coming in was not of sufficient quantity to make the process from brown grease to biodiesel an economical option. Another option the team considered was including the brown grease in the pyrolysis step to produce more bio-oil and using it as a fuel source to generate heat for some of the other processes such as drying. This was found not to be a worthy option when compared to the cost of electricity and also the possible price of just selling the brown grease by itself, which could give the buyer the option of potentially making a different product in the future. Another option the team considered was selling the biochar in bulk for land application This was a viable option because it did not require very much time or labor to sell in bulk. However, the added revenue from making it into a potting mix was high enough that it was better. Here are the links for the sources used in the video so far. Thank you very much for watching. This has been Anthony Zadoorian for the Repurposing Grease Trap Waste Project.